Right. Good evening. Welcome back to Applications of Calculus 2. We are looking at um, mixing problems, differential equations. Okay, so let's go ahead and read this to you. We have a 500-liter tank. They're mixing chocolate milk into this tank. Okay, it contains 460 liters of milk and 40 liters of syrup initially. Um, Syrup and milk are added to the tank at a rate of 2 liters of syrup per minute and 8 liters of milk per minute. The mixture is removed at 10 liters per minute. So it's going in at 10 liters per minute, and it's leaving at 10 liters per minute. We're going to say, assuming perfect mixing, which you kind of have to do because this is part of the way that works. Um, so assuming perfect mixing, construct a function s of t given the amount of to say how much syrup is in the tank at any particular time. Okay, so let's go ahead and figure out what we're going to do here. So again, just like with all mixing problems, we're going to go ahead and figure this out. So I want the change, that's a capital S recursive. The change in syrup over time is equal to, we'll say this is the amount in, so the amount of syrup coming in. So we'll just go ahead and we'll say syrup in minus syrup out. Okay, and that's what we'll go ahead and figure out for our differential equation. Okay, so let's go ahead and we'll keep our delta S over delta T, and we'll say, okay, how much is coming in per minute? So we have 2 liters per minute, and then what we're going to say to come out, I'm like, well, I don't know how many liters we have, but we have whatever number of liters is in there. So we'll say S divided by the 500. Okay. So we'll go ahead and do it that way. So we have 2 liters going in. We have S liters of syrup out, and it's liters per the whole vat. Okay. So that's how much liters of syrup is leaving us. Okay. So we can go ahead and do that. Okay. Let's go ahead and construct our differential equations. So we'll go ahead and we'll say we have S prime is equal to 2 minus S over 500. Okay, I'm just going to quickly, what is 1 over 500? Because I don't want to deal with a fraction, but we'll just go with 1 over 500. This book is very happy with 0.002. That's what they like to do. Okay, so we'll go ahead and rewrite that and we'll say this is S prime equals 2 minus 0.002 S. Okay, we'll put the leading zero in there, and then we'll go ahead and figure out what needs to be done for this point. I'm going to move the 0.002s over to the other side. So we have S prime equals 0.002s. We just added it to both sides. Actually, not equals yet. So we'll go ahead and do that, and we'll add this, and we'll say this is equal to 2. Okay, all I did was move this guy to the other side of the equation. All right. Well, would you look at that? It's a first order linear differential equation that would do well if we had an integration factor. So we're going to go ahead and say rho is equal to e to the 0.002 dt, because this is per time. Okay, going back up here, it's per time. Okay, so we can go ahead and integrate that. So this is going to be rho equals e to the 0.002 t. All right. And this is what I'm going to multiply both sides of my equation by. So we're going to say this is S prime. We have 0.002. Oh, no, we don't. We have e to the 0.002. We don't have anything with 0.002 yet. Let's go ahead and reset this. So we have e to the 0.002 t times S prime plus 0.002 e to the 0.002 t times s. And this is equal to 2 times e to the 0.002 t. You can put the leading zero in if you really want to. We probably should, but we're not going to do that right now. One of the things I want to do is I want to double check. I think this is a product rule. I think this is a result of a product rule. Could I say that this is some derivative of S times e to the 0.002t. Okay. Now, you could check this out. Say, okay, what if I took this derivative? Derivative of the first, s prime, times the second, 0.002t, plus the first times the derivative of the second, 0.002, e to the 0.002t. That's why I wrote it the way that I did, is because I want to double check to see what's going on. And if I rate those constant times the e, it makes it real obvious to me that this is a differential. Okay, this is the end. This is the result of a product rule. So I took the product rule. Does this look familiar? And I'm saying s prime e to the 0.002. Hey, check. This guy is the right thing here. And then we have 0.002 e to the 0.002t times s. So they're in a slightly different order, but all the pieces are here. And I'm going to say, you know what? This is the result of a product rule. This is the derivative of s times e to the 0.002t. And we're going to say this is equal to um, 2 e to the 0.002, e to the 0.002t. And what we're going to do is we're going to integrate both sides. And I'm going to say, okay, fundamental theorem of calculus says we take the integral of something we differentiated. We just come back to s e to the 0.002t equals, and now I've got to integrate this. We have 2 e to the 0.002t divided by 0.002. Okay, because we're trying to integrate e to the kx. So again, we integrate e to the kx, we get e to the kx over k. That's exactly the rule that we're using. The way that I also like to do it is like, what if I take this derivative? We get e to the kx times k. We had it over k here. And the k's cancel. We get back what we started. We integrated. We took a derivative. We ended up with the same thing. Good. All right. So the only thing I'm going to do now is say, what is 2 divided by 0.002? Okay, it's going to be 1,000, but we'll just say 2 divided by, or 10,000 rather, 2 divided by 0.002. Okay, just to kind of double check what's going on there. It's 1,000. Okay, so we have s e to the 0.002t equals, this canceled. We have 1,000 e to the 0.002t plus c, because we just integrated. Don't forget constant of integration. It's really important for problems like this. Okay, now we want to get s by itself. So what I'm going to do is I'm going to multiply both sides by e to the negative 0.002t. When the bases are the same, so this first thing, we're going to distribute it to this piece and to this piece. When the bases are the same, we add the exponent. So we have 0.002t here minus 0.002t. So that's going to be a 0, e to the 0. So we have s equals, this is going to be 1,000 plus ce to the negative 0.002t. Okay, and now we have to go back up to the original part of the problem. So they gave us a whole bunch of information about how much syrup was in the tank originally. We'll say when t was equal to 0, how many liters of the syrup were in the tank? We have to go all the way back up here and say, okay, when we first started, we had 40 liters of the syrup in the tank. So go all the way back down here. So when t equals 0, s was equal to 40. All right. And we're just going to go ahead and deal with this. We have 40 equals 1,000 plus c, which I don't know, e to the negative 0.002 times t was 0. So 0 times 0.002 is still 0. E to the 0 is 1. So we have 40 equals 1,000 plus c, technically times 1. You don't have to write that down. We're going to subtract out our 1,000 on both sides. Okay, and we'll have c is equal to, and we'll say, what is 40 minus 1,000? So 40, there you go, minus 1,000. There we go. And we'll get 960. So negative 960 equals my c. So when I'm getting ready to solve the problem here, write down my function. We have s is equal to, we're going to have 1,000 minus 960 e to the negative 0.002t. All right. Now, I'm going to say hold on for just a moment. Um, we'll go ahead and deal with this. So we're going to go ahead and, yeah, you can't really do this because you guys won't have the ability to actually deal with this. But just to show you what it looks like so we can get some kind of an idea of what's going on here, I'm going to bring up Desmos. You can't do this on an exam, and I'm sorry for that, but we'll go ahead and we'll look at this. Open the graphing calculator. So I'm just going to say y equals, so y equals, somewhere we could say y equals. Okay, here we go. So we're going to say y equals, okay, y equals, and we have 1,000 minus, so we have 1,000 minus 960 e to the, where's my caret button? I went e, sorry, 960 e to the negative point zero, e to the, good Lord, e to the negative point 0002. How about zeros? 0002 t, t. There we go. So we'll go ahead and take a look at that. Um, so we have to go through over here. So really what we care about is just the time when t is greater than zero, because time is going to have to be greater than zero. So let's go ahead and shrink this guy down. If you had to do this on a calculator, this would be delightful. Because the scalings is so much, we can see what happens. So at t equals zero, we're at 40, and then this curve gives us like how much time has passed and how many liters of syrup are in the tank at any one particular time. And you can see this kind of gets bigger and bigger and bigger until it gets to almost 1,000. Okay. So that's what we're going to be able to do for that. So just to give us an idea of like what this thing looks like, the concentration is going to go up, up, and up, and up, and up. We could look at this as t goes off to infinity. Let's go ahead and get rid of you. Okay. Um, go back to this thing. As t goes off to infinity, we're going to end up with 1,000 liters of syrup in here. Does that make sense? Um, let's see. How are we adding this stuff? We are adding 2 liters of syrup per minute to a 500-gallon tank. Does it make sense that we're going to end up with 1,000 liters of syrup if we let this if we let this concoction go long enough? Okay, and that's kind of what that works as. Okay, so that's what we're going to go with this. Okay, just to kind of check what's going on there. And then again, at t equals, I could say what happens after an hour, what happens after 2 hours. So we could say 120 minutes, what happens after 4 hours, t is equal to 240 minutes. Plug these values in, and we can get the amount of syrup that's going on in there and say, okay, well, that's how we're going to make our chocolate milk. Okay, so with that, I'm going to say thank you very much for watching the video, and good luck studying. These are called differential applications, different applications of differential equations, mixing problems. Okay, so we'll go ahead and look at that. Practice these. I like to see the whole setup when I ask you the exam for the thing. And yeah, that's fine. Okay. And we'll go ahead and cut you off for that. Okay. So I'll see you in the next video, and thank you for watching.